Today's lecture, lecture 39, is about diffusion in magnetized plasmas. If you recall the previous lecture 38, you will remember that we have taken up the case of collisional plasmas and we have discussed weakly ionized plasmas, but without magnetic fields. So, we have seen the effect of collisions in weakly unmagnetized plasmas, where the problem was stated like this, that we had considered the collision of charged particles with neutral atoms. There was a dense gas of neutral atoms in which the charged particles exhibited a random walk process. Today we are going to take up weakly ionized plasma once again, but now it is a magnetized plasma. And if you remember, last time we had not discussed fully ionized plasmas. This time we will also take up fully ionized magnetized plasmas and describe the effect of Coulomb collisions and find an expression for the diffusion coefficient, which we have already defined in the last lecture. So, we will study plasma diffusion across magnetic fields. And why is it important? It is very important a problem in controlled fusion research. It has been found that the rate of plasma loss by diffusion can be decreased by applying a magnetic field. Today we are going to see how this is done. Let us first take up the case of a weakly ionized plasma, a weakly magnetized plasma. So, the weakly ionized plasma is in a magnetic field. Qualitatively, you know that because of the magnetic field, there is the V cross B force on the charged particles in the plasma. So, we can say that the motion and therefore, the diffusion of the particles parallel to the direction of the magnetic field is not affected by the magnetic field, because the V cross B force is 0 when V is parallel to B. In the absence of collisions, the particles move in circles in the magnetic field and in a helical path in the magnetic field, and the guiding centers are bound to the lines of force. So, no diffusion occurs in the direction perpendicular to the magnetic field, across the magnetic field. It is a situation like this figure. Here I show you charged particles in a magnetized plasma, a single charged particle motion in a magnetic field. It is following a helical path. It is bound with a line of force in the magnetic field. The path of the plasma, path of the electron or a charged particle, here this helix or the helical path is the path of the charged particle. It gyrates about the same field line until it makes a collision. This is a collisional problem that we are taking up. So, a charged particle will gyrate about the same field line till it makes a collision. And what happens when it makes a collision? The orbit of the particle is disrupted, and a random walk, we can again take it as a random walk type of diffusion. So, what happens is collisions abruptly change the velocity of the particle gyrating around the field line. So, the direction in which the particle moves is changed, and therefore, the position of the guiding center is also changed. You can understand this better from this figure. Here there is a particle gyrating in around field line, and let us say the first figure shows you when you are looking at the particle in a transverse direction. So, you see a circle and you see the original velocity. At this point, the particle collides with another charged particle. So, the velocity changes direction. This is the direction of the new velocity, the red arrow, and therefore, the guiding center shifts. This is then the new path around which the particle gyrates, the new circle, this circle, and the guiding center shifts from this point to this point. If you look at it from a distance, then the lower figure shows you what is happening. Here is the original path of the charged particle, it is gyrating about a field line. Now, look at this particle in the plasma. Say the electron, while gyrating about the field line, collides with this particular particle. What happens? The direction of its velocity changes, and so now it gyrates about a different field line, and the guiding center shifts. So, the charged particle has moved across the B field because of the collision. This is how particles diffuse in a collisional plasma in the presence of a magnetic field. Let me just demonstrate this again to you. This is the path of the original particle. Now, it collides as it is moving along this path, it collides with the particle here in the plasma and acquires a different velocity in a different direction. So, it starts gyrating in a different path, though in the same direction, along a different line of force, and the guiding center shifts. So, there is a shift, there is a diffusion of the particles across the magnetic field. So, this is how diffusion takes place in a magnetized plasma. The charged particle continues to gyrate in the same direction after collision, as you have seen in the previous graphic, but the position of the guiding center shifts and the guiding center undergoes a random walk. But the mean free path now is equal to the Larmor radius instead of the lambda m. Earlier it was the charged particle that was undergoing a random walk. In a magnetized plasma, it is the guiding center which undergoes a random walk, and the step length is the Larmor radius. Now, diffusion across the magnetic field can be slowed down by decreasing the Larmor radius, that is by increasing the magnetic field. So, we have to find out the diffusion coefficient for a weakly ionized plasma in a magnetic field, for the diffusion of particles in a weakly ionized plasma placed in a magnetic field. As usual, we will start with the equation of motion. Since the motion in the direction parallel to the magnetic field is absent, there is no motion in the direction in which V is parallel to B. Therefore, we will study the diffusion in a direction perpendicular to the magnetic field, across the magnetic field, writing the equation of motion in a plane perpendicular to the magnetic field. Once again, we take the steady state isothermal plasma, and write down the equation of motion. It is written here, Mn dV perp upon dt is equal to plus minus En E plus V perp cross B minus kBt grad n, the density gradient, minus Mn nu V perp, the momentum loss. So, this is the equation of motion for the perpendicular component of the velocity. Once again we solve it under certain assumptions, the way we did for unmagnetized plasmas. We take the collision frequency to be large, so that in comparison to this term, the term dV perp upon dt can be neglected. For simplicity, we take the electric field to be 0 and the density gradient in the positive x direction. You will see that the results arrived are the same, but the algebra becomes pretty simple. So, let us see what this equation of motion reduces to under these assumptions. The term on the left hand side is 0, and we have also put the electric field equal to 0. So, we are left with 3 terms now, the V perp cross B, the density gradient which is parallel to the x axis, and the momentum loss term. From here we can write down an expression for V perp by taking the last term to the left hand side. We are left with the 2 terms V perp cross B and the density gradient in the x direction on the right hand side. Once again we follow the same process and divide the entire equation by Mn nu, but this time the V perpendicular has 2 components, x and y components. So, we write the x and y components of the equation. Now, here we have a cross product V perp cross B, which you know very well is minus Vx j cap plus Vy I cap B. If you apply the definition of the cross product, then you can simply write the equation of motion for the Vx and Vy components. You just take the x component of V perp and the x component of V cross B term, and you get this, the density gradient term is already there, and you get this term from the x component of V cross B term. This is the x component, the Vy I cap. Similarly, the y component you do not have in the density gradient, so you are left with only one term. Divide by Mn nu, you get expressions for Vx and Vy. What is the difference between these two expressions from the earlier case? These are now coupled equations. You have Vy in the equation for Vx and Vx in the equation for Vy. So, how do you solve this? You have to get an expression for V perp and you have to write the equation, continuity equation. So, what do? You just, before getting into the algebra, we will also make use of the fact that d, the diffusion coefficient, is kBt upon m nu, and we will use the definition of omega c equal to Eb upon m and write Vx and Vy in terms of d and omega c. So, in terms of d and omega c, obviously you can see that the expressions are much simpler. Now, we substitute Vx in Vy, Vx from this equation in Vy, Vx from here in Vy. What do we get? It is a matter of algebra. We have said Vy is equal to minus plus omega c upon nu Vx. So, you substitute Vx, here is minus. So, minus plus and this is minus. This becomes plus minus omega c d upon n nu del n upon del x minus omega c square upon nu square Vy. So, this equation you have Vy alone and the density gradient. Now, you take this term to the left side minus omega square upon nu square Vy and you get Vy equal to Vy multiplied by 1 plus omega c square upon nu square equal to plus minus omega c d upon n nu delta n by delta x. Once again we use the definitions omega c and d and we write this term omega c d upon nu here, the coefficient of the density gradient. Do some simple algebra, substitute for d, multiply and divide by EB. So, we can express this as omega c square upon nu square kBt upon EB. This is all so that the final expressions look simpler and elegant. So, we rewrite this equation for Vy as Vy 1 plus omega c square tau square, which is nothing but 1 upon nu square. This is what we have used, and omega c d upon nu as kBt upon EB omega c square upon nu square. 1 upon nu square we have written as tau square. So, we get an equation for Vy which does not contain Vx. It is a result in terms of the density gradient. We divide the expression by 1 plus omega c square tau square and we get an expression for Vy. Similarly, by substituting Vy in Vx here, this now in this Vy is equal to minus plus omega c upon nu Vx into the expression for Vx, we can again derive an expression for just Vx the way we have done for Vy. Vx 1 plus omega c square tau square is equal to minus d upon n del n upon del x. So, we get two equations for Vx and Vy which are now uncoupled and they are now given in terms of the density gradient. This is what we had done for unmagnetized plasmas also. We have a term d upon 1 plus omega c square tau square here. Now, we have to write an expression for the perpendicular velocity vector, which is again reconstituted by adding up the x and y vector components. So, although the expression looks a bit involved, you will find that this is simply the Vx term, this is the Vy term, and we define a new quantity called d perp here and another quantity Vd here, so that the expression for V perp becomes simple. It becomes minus d perp grad n upon n. Grad n is simply in the x direction. So, del n upon del x can be written as grad n plus another term Vd upon 1 plus nu square upon omega c square. This is what we have defined to write the second term in a simple expression. This is what we have defined. D perp equal to d upon 1 plus omega c square tau square, and Vd equal to plus minus kBt upon Eb 1 upon n del n upon del x j cap. So, this particular term, except for this, the frequency dependent term can be written as Vd, and if you divide this whole thing by omega c square tau square, you can write the expression as 1 upon 1 plus nu square upon omega c square. So, the d perp is the perpendicular diffusion coefficient for weakly ionized plasmas. And what is this term Vd that we have defined? It is actually a diamagnetic drift term. Right now we are not going into the diamagnetic drifts across magnetized plasmas. We will be concentrating on the diffusion coefficient. So, we have found a diffusion coefficient for magnetized weakly ionized plasmas as d upon 1 plus omega c square tau square. You can see that it depends on the collision frequency, because you have tau here or 1 upon nu square, and also on omega c square. So, let me summarize this discussion on diffusion across a magnetic field for weakly ionized plasma. We have derived an expression for the perpendicular velocity term. We have found that there is an extra term due to the diamagnetic drift. Right now we do not pay any attention to that, and we have defined the perpendicular diffusion coefficient. The diamagnetic drifts are perpendicular to the gradients of potential and density, and these are slowed down by collisions with neutral atoms, because there you have the collision frequency. The diffusion drifts, on the other hand, are parallel to the gradients in density. The diffusion drifts are parallel to the density gradients. These are in the direction of the density gradient, and these are reduced as compared to the case when B is 0. When you have B, you have a term omega c here. So, the diffusion drift is reduced. However, the presence of collisions enhances this phenomenon of diffusion, because we can see that this term would be 0 if the collisions were absent. You have nu square d upon nu square plus omega c square. So, if nu were 0, d perp would be 0. There would be no diffusion across the magnetic field. This is in the direction of the density gradient. It is reduced as compared to the case when the magnetic field is 0, and these are enhanced by the presence of collision. The diffusion process is enhanced. So, this in a nutshell is diffusion across a magnetic field for a weakly ionized plasma. Now, we come to the case of collisions in fully ionized plasmas. In fully ionized plasmas, all collisions occur only amongst charged particles. In weakly ionized plasmas, you will remember the collisions were between charged particles and neutral atoms. Now, the collisions are between charged particles, and these are the Coulomb collisions or the Rutherford scattering that I have shown you last time. Now, if we look at the collisions between charged particles, there is a difference between collisions between like particles and collisions between unlike particles. For example, if it is an electron-electron collision or an ion-ion collision, the masses are about the same. What happens is simply that the velocities get exchanged, and the center of mass of the system remains just where it was. The guiding centers mostly remain in the same position. So, for our calculations, we can neglect this. There is no diffusion as such for, or very small diffusion for like particles collisions. Particularly for head-on collisions, you can remember from, you can go back to your college physics and you can see that the two particles of equal mass just exchange their velocities. And for other finite angle collisions, the center of mass of the system remains stationary, and so on an average such collisions produce small diffusions which we can neglect. This is the figure which shows the collision of like particles. This is one particle and this is the other particle. They are gyrating, they collide, and their paths shift in a manner that the center of mass remains the same. It is stationary. It is a 90-degree collision between the particles. Now, what is of interest here in the diffusion phenomena is the collision of unlike particles, collision of electrons with ions or ions with electrons in the plasma fluid. And here we take recourse to Coulomb collision and Coulomb collisional cross section. What happens in a Coulomb collision is that a charged particle, as a charged particle approaches an ion, it undergoes scattering and follows a hyperbolic path. If we go back again to our college physics, we can find out the path of charged particle scattering. In this figure, we have shown the collision at the distance of closest approach. This distance r0 here is the impact parameter. It is the minimum value of the impact parameter. So, it is called the distance of closest approach, and this is the electron path, the solid line. This is the original path of the electron, this horizontal line, and it gets deflected in the collision because of the presence of the ion. Now, in an electron ion collision, the mass of the ion is much larger than the mass of the electron, so that we can assume that the center of mass is at the ion and the ion remains almost fixed during the collision. The Coulomb force is simply between the two, if we do not take the atomic number into account. To keep things simple, we can write the Coulomb force as F equal to minus E square upon R square. If the velocity is V, then and the distance of closest approach is r0, then this force acts for a time r0 upon V. So, the change in momentum is just the average force multiplied by the time. So, you multiply E square upon R square by R0 upon V, we can put R equal to R0 there. So, this is the change in momentum, E square upon R0 V. And we are right now discussing large angle scattering when the Coulomb potential energy is equal to the kinetic energy of the electron. The scattering angle is 90 degrees, and at those scattering angles, the change in the momentum is of the order of momentum itself. So, we have an equation which gives us the change in momentum as E square upon R0 V, from where we get an expression for the impact parameter as R0 equal to E square upon mv square. And once again, using the classical total collisional cross section as pi r0 square, we simply put r0 square here, we get the collisional cross section as pi e raised power 4 upon m square v4, and therefore, the collisional frequency is simply n sigma v. We have defined it earlier, and this is equal to n pi e raised power 4 upon m square v cube. So, we have our collision parameters. Now, there is something which we need to discuss here is Debye shielding, which you have studied earlier in these lectures. Debye shielding imposes a maximum value on the impact parameter. As you know, in a plasma, the positive charges attract the electrons and repel the ions, and so a net negative charge accumulates around the positive charges, thus reducing or shielding the electric field due to the positive charges. On the other hand, electrons also have thermal energy, so they cannot just collapse onto the ions. So, there is an equilibrium which is established between the attraction, force of attraction of the ion on the electron, and because of the collision, due to collisions because of the movement of electrons away. So, due to interparticle collisions, Coulomb attraction and thermal motion comes into equilibrium, and the field of the plasma is shielded from any external fields. This is the Debye shielding. You have also studied the parameter Debye length, which is the screening distance over which the Coulomb field decays exponentially. So, beyond the Debye length, the Coulomb field of the charged particle falls very fast, and so within the plasma, electric fields applied to the plasmas beyond a few Debye lengths do not matter. The plasma is shielded. So, the upper limit of the impact parameter then becomes equal to the Debye length. So, we are considering a collision between R0 and the Debye length lambda d, and we have seen the parameters for 90 degrees collisions. For small so the maximum impact parameter is simply the Debye length. We have already written the collision frequency for 90 degrees or large angle scattering. For the small angle scattering effects, a small correction which is called a Spitzer correction needs to be added, and we will not go into the calculations because these are pretty involved. With this, we can now once again try and derive the coefficient of diffusion in a fully ionized plasma. Once again, we write the equations for both the species. Mn dVi upon dt is equal to Ene plus Vi cross B minus grad Pi plus Pie, and similarly the equation for the electrons. The last term in these equations, Pie and Pei, are the momentum terms, momentum gain caused by collisions of ions with electrons and electrons with ions. Once again, we will be making certain simplifications, and we will study steady state and isothermal plasmas. So, the term on the left hand side then becomes 0, and for isothermal plasmas we can write the pressure gradient in terms of the density gradient. So, the equations are somewhat simplified. We have En E plus Vi cross B minus kBTi grad n plus Pie equal to 0, and in the same way we can write the equation for the electron with Vi replaced by Ve, Ti by Te, and Pie become, instead of Pie we write Pei. Okay. From conservation of momentum, Pie is simply minus Pei, and in a fully ionized plasma, Ve nearly equals Vi. It is not exactly equal, you will see the implications. If you remember, P is Mn V nu I. So, in terms of the velocities, you have Pie minus Mn multiplied by Vi minus Ve nu Ei, Pei is minus Pie. So, you write that expression. Now, on physical grounds, we expect the momentum term to be proportional to three factors: the Coulomb force, since the Coulomb collisions are Coulomb collisions, density of electrons, density of scattering centers which are equal, and relative velocity of the two fluids. So, Pei, let us take Pei is proportional to E square n square and the difference of velocities here. We replace the proportionality constant by eta here. So, we write Pei as Mn Vi minus Ve nu Ei, and we have on physical grounds an expression for Pei in terms of eta, and if we compare the two, we get nu Ei in terms of eta, or eta in terms of the collision frequency. What is this constant eta? We can see that it is nothing but the specific resistivity of the plasma. How is it so? Let me explain very quickly. But before that, there is one expression for eta which we can also write by substituting for the expression of the collision frequency in terms of the mass and the charge and the velocity. We get an expression for eta equal to pi e square upon mv cube. And if we account for the small angle collisions, we have to multiply by a factor log lambda, which is the Spitzer correction. Again, let us come back quickly to the point why we call eta as the specific resistivity. If you go back to the equation of motion and put B is equal to 0 and KBTE equal to 0 in this equation of motion for electrons, for steady state you get a simple expression Ene equal to Pei. And since J is Envi minus Ve, we can write Pei is equal to eta E square n square Vi minus Ve equal to eta E n j, from where we get E is equal to eta j. This is nothing but the Ohm's law, and so eta is nothing but the specific resistivity. With this, we can now make a calculation for the diffusion coefficient for fully ionized plasma in terms of the specific resistivity. We write the equations of motion for steady state isothermal plasmas. For electrons, let us say, we get this particular equation. We have the electric field term, the V cross B, the density gradient and the momentum terms. We do a simple algebra and we write EVE cross B in terms of E gradient n and substitute for PEI here, PEI, right. We say that E is perpendicular to B, the density gradient is perpendicular to B and the electron and ion velocities are perpendicular to B. Under these assumptions, I have written down the equations again for ready reference. Under these assumptions, we write the equation and take the cross product of this equation and the magnetic field from the left, B cross E, VE cross B, and from the left you have this, you have this and you have this. In all three terms, you take the cross product of B from the left. So, on the right hand side, minus B cross E is simply E cross B. Similarly, we absorb this minus sign in the second term by interchanging the cross product and in the third term too. So, we interchange the vectors in the cross product and now we have to calculate the vector triple product. From your college physics, you know that A cross B cross C is A dot C B minus A dot B C. So, you can apply that result, and what do you get under the condition that VE and VI are perpendicular to B? You get the triple product simply as B square VE, right. It is a simple expression. Substitute that in the original equation, you get a simple expression on the left hand side, the right hand side remains the same. You divide then by EB square the entire equation. So, you get this equation in which you have divided the previous equation by EB square. So, E and E cancelled out in the first term, and here you have EB square in the denominator. This is simple algebra. You can repeat the same procedure for ions and write an expression for the ion velocity in terms of E cross B gradient and the momentum terms. These are the two terms for electron velocity and ion velocity. In these you have an expression for VE minus VI. So, we have to still do some more algebra. What we do is we subtract VI from VE, and we get an expression for VE minus VI in terms of grad n cross B, which we substitute again in these two equations. So, we get VE, all other terms remaining the same. The last term has another vector triple product del n cross B cross B. You use the same method to simplify the last term, but the triple product is this time different. It is A cross B then cross C, which is a different product. Apply this and you get a simple answer. Del n cross B is equal to minus del n B square. So, VE becomes, just substitute this term in the third term on the right hand side, you get an expression for VE. All other terms are the same. Having found VE, we substitute it in the continuity equation the way we did earlier and simplify del dot NV. This is the equation when we substitute VE. Here you will know from the vector identities that del dot del n cross B is 0. I have shown you the vector identity. Del dot E cross B is also 0 since E cross B is constant. So, this term is 0 and this term is 0, and we are left with two terms here on the right hand side. We are left with two terms. I have repeated this expression. In this huge expression, two terms are 0, this term and this term. So, we are left with two terms, one of which gives us the coefficient of del square n, and that is nothing, as you know, but the diffusion coefficient. This is nothing but the perpendicular diffusion coefficient. And since eta is m nu upon Ne square, we can write this diffusion coefficient in terms of eta as eta n kb Te plus Ti upon B square. This is the perpendicular diffusion coefficient for a fully ionized gas. So, we have been able to derive an expression for the perpendicular diffusion coefficient in fully ionized plasmas and weakly ionized plasmas in the presence of magnetic fields. let us compare quickly the d perps in both cases. You will note that they are proportional to 1 upon b square. So, as you increase the magnetic field, diffusion across the field is reduced. However, the difference is that for a fully ionized plasma, d perp is not constant, it depends on the density. Moreover, the specific resistivity is proportional to kT raised power minus 3 half. So, d perp in a fully ionized plasma decreases as the temperature increases, and the opposite is true for the weakly ionized plasmas. This occurs because of the velocity dependence of Coulomb cross section. The third difference is that diffusion is automatically ambipolar in a fully ionized plasma if we ignore like particle collisions. It is the diffusion coefficient for the entire fluid. No ambipolar field arises because both species diffuse at the same rate. So, these are the differences between diffusion in a weakly ionized magnetized plasma and a fully ionized magnetized plasma. For the sake of interest, I would like to show you a graphic showing the theoretically determined perpendicular diffusion coefficient d perp, this is d perp, on a logarithmic scale. This is the classical diffusion, which is the expected diffusion. We are taking a logarithmic scale and showing d perp versus collision frequency. There is an enhanced diffusion in this so called Plato regime. It's an experimentally observed situation, and it is still an area of active research for explaining this particular diffusion phenomena, which appears in a tokamak in controlled thermonuclear fusion. So, with this we come to an end of the discussion today on diffusion in magnetized plasmas. In this particular lecture, we have determined the diffusion coefficient for a weakly ionized plasma in a magnetic field. The plasma is also collisional. So, we have taken into account the effect of collisions in a weakly ionized plasma in a magnetic field. Then we have also determined the diffusion coefficient for fully ionized magnetized collisional plasma. So, this is all for today. Thank you very much.